Alright, video is recording now. Yay. Let me, that's down, we just need that one. Okay. So, we've been talking about how to do asynchronous design. So this is kind of day 300. So, on our first day when we looked at how we could use latches, and we looked at some of the problems. We discovered beyond what we've dealt with so far, there's also these things we call race conditions, right? And their race conditions can be critical or not. If it's a critical race condition, essentially this can cause us big problems because we don't know what's going to happen. We don't like to not know what's going to happen in our designs, so we've got to make sure we roll those out. Other race conditions, maybe not ideal, in a perfect world, but, if it doesn't matter what happens, the only question is, how many transitions really until then, right? And they could all end up at the same spot, but one could take one transition and one could take like 3, right? So again, not perfect, but that's tolerable, right? And then we always want to avoid glitches and other stuff. So generally, if we can do something very safe, like we would do with a KNAP or something, that's what we prefer that. Remember, a lot of what you have as safety features with other designs, like FPGAs, that requires a pocket. You can have a pocket in ours. So we really do not like the other types of designs that they don't have glitch removal inherent in the design. So KNAPs and Klein-Kluski and stuff of that sort is going to win the day for most of our asynchronous designs. We feel all good on that. Last time we talked about key and lock. Remember the whole idea of that was just write everything as if it was basically an enable, and then we can combine the enables to get our transitions. So that was one methodology. We said it doesn't create necessarily the fastest, but it is easy to do. That has some virtues to it, but not perfect. So we started looking at primitives. And we took a look at a simple way to do a primitive, and we just we introduced the idea of what are state equivalents. And we could look at the simple design we had done the previous time. We saw there was 2 states we could, in theory, combine. That's basically where we're at this point. What I'm going to do is talk about how we do state reduction in general, and then we'll take a look at ways we can try to make sure we get a design that avoids bad properties. Some of these are going to allow us to do things like picking different encoding schemes. Sometimes it's reducing states will make our life easy, and sometimes actually, splitting or other things states might actually make our life easy. So there's going to be a series of different options where this is where kind of your creativity and heuristics come in, and we'll show some legal safe ways to do this. So that's kind of today's goal. Let me start out with, last time I just kind of gave you a graph. Let me start with doing a graph in a slightly different way. So let's imagine I've got a bunch of given primitive states. A, B, C, D, E, F. So those are my primitive states. And let's say I've got some inputs here. We'll do 0, 0. We'll do 2 different input bits. Let's make sure I have the room there. 0, 0, 0, 1, 0. We will always do our inputs listed in gray code fashion because that just makes it easy on transitioning between these. So I'm going to do a slightly different way. I want different colors for these. That I'm going to build my state machine. I'm going to actually draw my state machine inside my table here. That may sound weird, but it'll actually help me in some ways. And I'm going to have a couple rules, right? I will follow the basic thing where I'm going to list, it's semi-drawing the state machine, right? I'm still going to follow my A goes to A, so that's stable. That much is going to stay on here. But I'm only going to draw those stable states. So let's say in this case, I've down the main column here, let's say I've got, whatever, these ones are all stable. Now, I'm going to do a slightly different convention here. I'm going to put my outputs after a comma. Inside here, you could make it after a slash. It's not a huge thing on these. So let's just say I have these, right? This is my state A, its output is 0. B, its output is 0. C, its output is 0. D. I'm not telling you what's happening in the other cases. These are stable states. They just kind of hold on where they're. Let's just say E, let's put it here, and maybe it's outputting 1. And I'm going to make F stable everywhere. Why am I going to want a state that's stable everywhere? Stable here to it, and it's very stable. Yeah, so this one, and it'll never leave, will it? No, it won't leave, and so in theory, it's like an application of like, hey, this is my end state. It could be an end state. That's a very good spot. If there's someone that's kind of get some input and let you know. Let's say again, I was dealing with something like some physics. They're looking for a series of ones and a bunch of checks. And then there's an end state to say, "Ooh, I saw the particles and you wanted and all these conditions in the right sequence to them or whatever." And then I'll have something external that resets this to be able to get back and start running the system again at some point. But it holds it. It could be an error state. Something bad happened, and I don't want you to recover from the error until I have an error handler. I just mentioned that there's a whole ton of reasons, but you can see there's good reasons. I've reached an end state, and I want to handle it first. It could be an error state. Usually it's something that I've got to hold it for a long period of time, and I want somebody else to do something to get me out of there that's not part of my normal sequence, right? I hit a reset or whatever else makes me happy. Now, what I'm going to do, I'm going to keep a lot of different colors and stuff. Let's see. Okay, I got red for this one. When I draw my transition arrows, I'm going to always draw them going over first and down. So like if A will go from state A to state B on a 0, 1, I'm going to draw it from, I had to have been in my stable spot, because otherwise it's just too likely to just randomly happen. And I'm going to do the horizontal first, because in theory, I was sitting there in my stable state waiting forever, right? And then an input came in and I reacted. Right? Yeah.
And the grid is the third to the right of the.
That's the output.
That's the output.
Yeah. Yeah, it makes feel very much slash there because we always put outputs into a slash. I don't like slashes because when I do these myself, I just write them really small, usually in like the lower corner or something, and a slash just makes it that much uglier. And it's just my eye tends to go to lines. I don't think that's true with most people, so I tend to try to avoid putting too many lines in because it starts getting confusing. That's really my whole reason. So I just did a comma here to avoid that. In most of these cases, I'm only going to worry about the transitions that don't involve races. So I'm not going to worry about going from 0, 0 to 1, 1. A is in the 0, 0. So the only two I'm going to worry about are these two. And let's say it goes to D. Fair? So if I'm in A, one way to leave that state, right, which is a 0, 1, and I'm going to have one way to another way to leave that state, which is a 1, 0. But I'm not specifying anything 1, 1 because now you have to do a race condition, and I don't know what's going to happen. So I'm just saying I don't even want to deal with it. So these are the only two functionalities I'm going to worry. Now, on these, I can take a look at each one of these in turn and say, what's going. So maybe I make B, and B can, right? It's in the 0, 1 column. It's nice and stable. If it goes to 0, 0, maybe it goes back to A, and maybe in 1, 1, which is its other 1-bit flip, I go to C. So notice again the input changes, and then I respond to it quickly. So that's the whole idea of these arrows. And I can draw, in this sense, this is, whatever. I'm just going to do some simple little pattern here, right? I don't care what you watch. I got something that's in here. But I'm kind of putting these in a nice, easy to follow way, right? Now, this isn't going to be my final thing. This just lets me kind of organize everything nicely when I'm thinking about it. And in a lot of these cases, there might be a bunch of user constraints that we put as single requirements. And so we can, each of these transitions comes from something that was identified as a functional use case. We talked with our clients, we found out what they needed, we turned what they needed into a functional use case type area. From those, I ended up getting these individual error trains or error rate transitions. So let's say we have those, and I'm just going to put some other stuff in for each of these. Maybe B can transition to F, or whatever, to A, um, whatever, E will let it transition to A or over to F on its either side, and we don't have to worry about F because it never goes anywhere. So I'm just throwing some arrows up here to kind of get something. At this point, not as concerned what those were. It's really that why the arrows appear is some customer requirement. You should always be building it in response to what's the need of the situation. I just want to deal with how do we do, once we have a graph, what do we do with it? So we've done a couple simple ideas. Now we'll just take a look at this and how to get them. All right, so I've got kind of my transitions that are on here. Now we want to say, okay, let's turn this into our more usual type of a graph once I have these, right? And again, this is kind of nice because I've mapped my states in some sense, and I've just directly drawn them on a graph, and I can think about how my flows are going. This will end up producing, let's see, we want to get to a true table at some point. So I'm going to take that and convert it into a more traditional looking table. All right, so I've got A, and again, I'm just trying to make my output small. Yeah. I've got over here now, I never listed at the top, 0, 1, 1, 0. Those are all my inputs again. All right, I've got my first arrow. If it goes to 0, 1, it goes to B. Now, at this point, I haven't specified a particular output, so I'm just going to put a dash there. It just reminds me, I don't care what the output is. I'm transitioning between the two. Pick it to make your life easy. Usually on most, unless there's a specific requirement, in which case I have something labeled on the arrow, I don't have to worry about too much. Now, I could decide to pick this to be 0 to try to force a more machine. Who knows? In this case, maybe that will make sense. All right. I've also got this one going here, and it jumps down to D. So I can say, okay, that's D. I'm leaving this one completely blank because I didn't put any requirements. That means I get to put whatever works for me in that location. And I'm going to pick whatever works for me, as in whatever's going to give me a good, stable result. Right? But there's no requirement on my behavior because nobody should ever want me to do that. So I'll just be handling some weird thing happen. What do you do? All right, so we'll go through the rest of these, right? Here is, so that was A, I should circle it. B, I should circle it, and I get a 0. And I can look here, and you see, if I go to 0, 0, I should go to A. And again, I don't care what that is. Right? If I go to 1, 1, I'm going to C. Right? So this is more getting to what you're kind of used to on states. Right? Right, on the next row, IMC, that's stable, output is 0. If I go to 0, 1, I want to transition to B. If I go to 1, 0, I want to go to D. All right. If I'm in D's row, I'm going to put my stable state in first. If I go 1 to the right, I'm going to go to F. And if I go, or sorry, to the left, if I go to the right, I end up here, and that's going to go to A. Okay, I have nothing on that. All right. E is stable here. I put it stable state in. It's outputting listed. If I go to my left, I'm going to A. And if I go to the right, I'm going to F. And then on F, they're all stable.
So,
So all I've done here, right? All I've done is I've just taken the graph, right? This one you can imagine I started off with something that had state A and it said on a 0, 1, I'm going to B, my type of thing. I had a graph with that. I could just copy all these down, right? But I also could have had these under the case of I need some stable state that's, a starting condition. Right? And it could be listed that way. And on a 0, 1 input, it goes to the second state. Right? And on a 1, 0 input, it goes to the So I could actually also just have a list of records and a bunch of requirement actions. So it's sometimes nice to just redraw the graphs instead of drawing them in this way to just kind of draw the table. You can just go between them and do the error. That can lead to a nice, easy way to turn use cases into them. Does that make sense? So this is just really kind of an intermediate way you can do it, which can sometimes help you visualize. Usually when you start off with like individual text lines that describe each error. Right? So I find it easier to draw them on a chart than a lot of other people do, right? Because it just keeps things in order. And I can also at that point make sure I'm not worried about the race conditions in the input, which is going to be harder to see that in a area. So rather than generate the graph in an open form and then convert it, I kind of tabled it so I could check to make sure I didn't have races on it. Yeah.
trying to understand once you
Yeah.
circle, like for an row D, is it like on each corner where it's kind of,
So see the arrows,
yeah.
right? The ones that are not circled are not the stable states. They're actually telling you the arrows. For instance, on row D, right? I've got row D here, row D here, right? So if I look, the first arrow off D, right? I see this arrow off D. If, right, I'm at this stable spot if the input is 1, 0. At some point, somebody can transition my input to 1, 1. So I'm assuming I was stable at D. I went to 1, 1. What do I do? Do I stay at D? Do I go somewhere else? Well, the arrow tells me I go to F. So on here, I was stable at D on a 1, 0. When I go to 1, 1, it tells me go to F. So all these letters are doing is encoding those errors. I've just turned the arrows into a letter code that says, to what new road does it jump to? Then that's the vertical part of the arrow. Does that make sense? So you can look at any one of these, right? The other one here, right? This other red arrow. I jump over to 0, 0 and I go to A. Right? If 1, 0 got switched to 0, 0, it would go to A. So those other ones are only encoding the arrows. Yeah.
So the blank spots that we have are like inputs that we are caring about?
Well,
Or
right now, we're saying we don't want them to happen, right? So when I'm taking my use cases, right? So in some sense, it's in the description of a problem. I just made up here just trust. So I wasn't trying to model a particular problem. Plus, it often just, like, if you got a toy problem, I have to spend most of my time explaining the toy problem rather than what I'm trying to teach you to do, just have to reduce space. Okay? So this is just somebody gives it to me. In some case, there has been a process where I was working through and understanding what the problem was. This is all that, how do you get customer requirements, right? Then you have to turn the customer requirements into a functional system. Okay? They're asking you, their requirements are saying, I need a system that does this. The functional description says, what is this, right? Under this case, what do I do? A function just takes a series of inputs and gives you an output. So it should always behave that way. So that's in essence what we're trying to encode in this chart, right? So like I've got maybe F is an error state, let's just say, and E is some intermediate thing that's going on. A, B, C, D are some progression of important values depending on the input. And under some cases, I might have to go to, this is a weird case that needs to be handled, right? Maybe E is a recoverable weird state that F is, or whatever, right? So we've got these different states that I can go to and jump between. Does that make sense? It's kind of like a first cut on these of why it was. So I had some list of things that said, hey, state A is going to hold 0, 0 or whatever, right? But from this, we want to make sure that we don't ever have input races. Because remember, input races can create problems for us too. So when we write our specs and we're looking at how am I generating these requirements, what my system has to do, I don't want to require some transition to be dependent on input rates, because then I don't really know what's going to happen based on my inputs. So I have not encoded the spots where there are input races. So if you notice in every one of these, right, I only did the one, and remember these wrap around, so 0, 0 is right next to 1, 0, right? It's like a piece of paper you can fold into a tube. So I can say, hey, look, there's no race to go to this square or to wrap around and go to this square. But from 0, 0 to 1, 1, that's a race condition, right? Inputs. And I don't like that. So I'm deliberately not touching those because I just don't want to do those. I don't want to make part of the requirements. Now, I'm going to put something in there, but I don't want it to encode the logic that my user needs, and it's an almost never going to work situation. Does that make sense? I mean, if that is a case where we're saying, hey, we've got to see this kind of weird transition, then maybe. But I'd rather actually put a series of things, right? I see a 0 to 1 transition here, and then I, see some, that same thing turn back off again an instant later. I can encode that by state at every little step. So I'd rather encode that type of a sequence than trying to say, and they luckily magically switched at the same time. It just won't happen. So I'm going to assume that that's nigh impossible to get the default switch. And so that's why I left these ones off. Now realize there might be some user cases where they don't have a condition that has to happen under there. You could have some cases that could be a legitimate transition, a one-bit flip on an input, and it just doesn't matter to what their requirements are. Right? Then I leave it blank again because now I get to pick whatever makes my life easy. I mean, I can decide to make it stable, I can make a transition somewhere else, whatever. Right? So I don't want to put them in when I require those races, things of that sort. Does that make sense? And there are some, you might find some design where somebody's making some requirement of that sort, but always be careful when that happens. All right, we feel comfy with this. Right? I just had something which we said came from users. We just kind of drew the graph in the table. And then I encoded the stable states by the circles, right? And I did all the arrows by these non-stable states. Boom, done. I've got my first table of primitives. And this could be turned into like a K-map type thing for circles. But we're not ready for that yet. Looking at this, can you tell whether or not any of these states are needed? Can they pay? Things of that sort? It's kind of hard to tell. Okay? So the next thing we want to do is to see, do I need all of these states, right? Now we've coded what they want, how can we handle it, right? And if you remember, what was our basic condition to say two states, could be merged?
Two states can be merged if you go start in one room, go to the next room, and say, wow, this looks the same.
Exactly. You can't tell, right, from looking on the outside where you were at by any sequence of inputs. So if I'm in two different rooms and you will never tell which one I was in, then it already didn't matter which one you were in. Right? So that's kind of our idea, which means the outputs are what you're looking for, and I can move to other rooms. If I ever move to a room that gives different output, then it could have been told that I was in a different room. I could, in either of those rooms, I could give whatever input sequence that in one would give me a 0 and the other one would give me a 1, and boom, you know where you were before. Does that make sense? Okay. So we want to check this. Now, one way you could do it is we could make a gigantic matrix, right, that lists all the A, B, C, D, E, F, right? A, B, C, D, E, F. And we check, right? We could, right, put in all of the little lines and we could see which ones are compatible with which. Right? If I made a great big chart of this, though, some of these checks are unimportant. Can you tell me which one of these are not needed as checks? What? F to what? Okay, why?
Because that's a single table.
Right? Okay, in this case, you know it's stable. What if you didn't know anything about the graph? And I'm just showing you, here's a bunch of states. Which ones do you need to look at?
You it's a head. So I'm going
So I ultimately have to compare all of them. But do you need to see in my chart here, we've got A, B, C, D, E, F, A, B, C, D, E, F. Do you need to check and see if A is equal to A? What?
because A is green and that's A.
If, yeah, you don't have to see if you're compatible with yourself, you obviously are. Right? You have a deeper problem. Right? So, is there any other ones besides checking is AA?
A, B, B, C, C, D.
Okay, so can you simplify what I can do?
Yeah, did forward.
How can we remove the diagonal inside? Right? Because the diagonal checks to see all the states that are equal to themselves. You know, anything along the diagonal check, does A equal A, does B equal B, C, C, F, F, all the ones on the diagonal, you do need to check. They, they're, they match on. Now, somebody said the lower, right? Why do I not need the lower?
It's just the same in the other order.
Yeah, so I could take the lower or the upper because they're identical. They're just a mirror flip about that diagonal. Right? If I had, for instance, B compatible with A, that also means B is compatible with A, right? The two ones cross the mirror. That's true for all of them. So I only need either the lower or the upper. Do we agree? And it doesn't really matter which one you pick. So I just do this as an aside because it's going to look odd. I'm going to pick the lower one, and that's just because my letters are like sexy, so it makes my life easy. Right? But it's obviously you can pick the upper if you want to draw your things different. Right. And notice I'm going to start at B on the vertical column. So I start the second state on my doing the rows, right? And I'm going to start the first, but I won't need the very last. So when I'm drawing these, I will have B, C, D, E, F, and then A, B, C, D, E. So now I'm going to formally draw all of those lovely little boxes because this is that lower part. This just lists everything I need to check. That's all of this chart. This is a very standard looking chart. If you look at any book that does state reduction in digital logic, they all do this chart. Okay. What I'm going to do is I will put a check mark if they are compatible. I will put an X if they're not compatible. And if I don't know this one, I'll write all the conditions necessary to make them compatible. Okay? Just the basic thing putting out right in the boxes makes sense. Check means it's good, they're compatible. X means they are not compatible. Okay? And if I write something inside there, I'm just telling you what needs to be compatible later. Because there's like this whole cascade of input sequences, so it'd be a pain in the rear. So I'm only going to check the most simple conditions first, and I'll find whatever ones are just innately not compatible. But on all the other ones, I have the conditions that tell me what needs to happen, and then I can take those first level things and come back and modify stuff, and I'll keep doing that until I get conditions. Does that make sense? Okay. So let's take a look at our chart. I want to see, is A compatible with B? So I'm going to be checking this chart. So the first thing I'm going to do is the easiest. Are the outputs compatible? Well, I've got a 0 with anything you happen to want, right? And anything you want with a 0, right? Who cares with who cares, who cares with who cares. On the inputs, are they good? Or sorry, whatever the outputs are they good? The outputs are good. So I don't have a problem yet. Can A be A? Now we check to see, are the state transition letters? Where is it going in? Is that compatible? Well, that's totally fine. B is B, totally fine. Anything with C, anything with D, right? That's fine. These are compatible, right? I don't need to merge them, but theoretically I could merge them if I so chose. Does that make sense? Okay, let's check A to C. A to C, well, this has no requirement. 0 to nothing, nothing to nothing, 0 to nothing, nothing to nothing. No problems here, right, on the outputs, right? A to nothing, now we check our states, no problems. B to B, is that a problem? Nothing to C, D to D. These are compatible, aren't they? I could merge them in theory if I want. Now notice, if I merge A and B and A and C, I'm going to also have to worry if B and C are compatible. But we'll show an easy way to check this later. These are just showing me pairwise can they be merged, not necessarily combinations. Let's take a look at A to D, right? A is A, fine. Oh, sorry, I should do my output 0, nothing, nothing, 0. So output Y is good. A to A, B to who cares to F, D to D. So are A and D compatible? Yes. Yes, indeed they are. Right? All right. A to E. So now I look, no requirement, 1, nothing, 0. Totally fine on the inputs, isn't it? A goes to A. Oops, sorry, I just did wrong one. All right. Sorry, A to E. I compared my wrong columns. 0, nothing to 1, nothing to nothing, nothing to. So it's fine on the outputs. A to A, fine. B to E. Well, I don't know. What if B and E merge? Right? So I don't know right now, but I have to check and see, does B equal E? So I'm going to just list whether the two are equal by writing the two letters down. I strongly advise you write them in alphabetical order. I'm just asking if these two are compatible. They're tough enough to find, let alone if you have to find the flipped pairs. So make your life easy, write them in alphabetical order. They're much easier to locate. But now I've got a condition I have to write in, and I don't know whether it's true or not yet. But if that's true, then I'd be able to do it. Any others, nothing to F, D to nothing. No problem. So that's my only condition, but I don't know if it is yet, right? A to F, right? Well, I've got 0 to 1. That is strictly not possible. I have to check it. Right? Because in the very first square, one of them wants to output a 0, the other one wants to output a 1. Good? All right, then I go to the next one, right? I want to compare B and C, right? Well, no requirement, 0, 0, all fine on the outputs. A to nothing, B to B, C to C, nothing to D. Is there any problem with B and C? Sorry, yeah, B and C? No worries, all right? Again, you don't have to merge them. It just says there's no problem with merging. B to D, right? So no problem, no problem. The outputs, fine. And then A has to be A, B could be anything. C to F. C. Fine. So now I have to write that in. CF. And nothing to D. We're totally good. That's the only requirement. B to E. Now, if you notice, B has to be a 0 here and E has to be a 1. So what do we know? Boom, instantly gone. Right? And B to F. It's going to be the same problem, 0 to 1. Good? Then I start going through, right? C and D. Right? So C and D, right? No problems, no problem, right? All the zeros obviously work. I need a C equals F. That is my only requirement, right? Now you notice that is the same thing that's happening with this other one. All right. How about C and E? Right? So C to E, right? I check. There's no problem with that one, right? So no problem with the outputs. Nothing to an A, no worries, right? B to E have to be the same, right? And C has to be F. And you can see this is fairly sparse, right? So, it is, oops, I wrote down the wrong column, CF, right? So, sorry about that one, right? So, B to E and C to the F are both requirements for C and E, so it has to be written in the CE area, right? No other ones. You can get a whole bunch written in here. That's it. Okay, so now that one has two requirements that have to be met. C and F. Well, I can look in the 0 and the 1, so it ain't working. All right, go to the next square, D to E. All right, comparing here, outputs, no worries. A is A, nothing D, F to F, D. So what do we have for D and E? Well, D and E are totally fine. They're compatible. All right, D to F. Yeah, because we got a 0 here and a 1 here, no go. How about E and F? Well, that's fine, right? But watch, A has to be F, right? That's one of my requirements, right? That one is my thing. I'm checking F, right? So I just have an AF. I'm not doing any analysis of where you're getting answers. This one is just write down directly where the components on the table. I don't attempt to jump things. It's too easy to make a mistake. I'm going to do my next pass. So I know some information. and I can go between these and check and see, right? So I can check BE, right? So I can look and say, does B and E, are they compatible? And what do I see in X? So, boom. And I'm just doing it in a different color here. It may not show up so well on the screen. Sorry about that. But it is distinct. It's red on this one. I'm just doing it in a different color so it's easy to spot. Can C be F? I can look, can C be F? No, it can't. So that cannot happen because its requirement can't be that. All right? We already see on this one C and F and B and E, so we can, that one requires C and F, that can't happen. And then I have an AF, well, A to F, that can't happen. So I go through, I've now removed everything that's ended up being either a check or an X. There'll be one other case that could happen where one says like, A can be, B can combine with one combo, and I can check in the AB area, and it might say whatever that one was, right? So I might have a thing, can A be B? Well, only if C equals D. And can C equal D? Well, only if A equals B. Right? They're mutually dependent, the cycle like that, and you could, in theory, set both of them in UB1. So then they become mutually compatible. That's the only other case I have put here, and I'll have another example which will show that for you. Now, if you looked at this chart, right, we're now done. Can I just merge all of these states? Anybody who's a check mark, I merge them? No. So now the question is, how do I, right? This is pairwise compatibility. It's not complete compatibility. So what I find to be a helpful, and this is another one of those kind of neat graph things, is to turn this into a compatibility graph. So you draw like a big circle, and we've got what, 6 states? So I'm gonna put these spots on them. I'm gonna label them A, B, C, D, E, F. Fair? Now, I'm going to draw lines between them if there's a check mark. So for instance, A and B, there's a check mark, so I'm going to draw a line. All right? A and C, there's a check mark. I'm going to draw a line. A and D, check mark. I'm going to draw a line. Fair? I go to the next one. B to C. There is a check mark for B to C. Draw a line. No, there's a next. There. One more. D to E. All right? So this graph summarizes this table, but I submit to you this is much more readable. If I merge all these states, I'd be forcing A to be B, B to be C, A to be D, right? Which would also make, since I merged A to B, if I merged A to D, I'd be forcing B and D to become the same. That would work. So you can only reduce states in a way compatible in here. You can't force things without connecting lines together. So I could, for instance, decide, okay, this is actually let me pick a different color. I could merge these three, couldn't I? They're mutual. There's a completely connected graph between those points. That would be totally fine. Could I merge D and E under that scenario? Yes, I could. That would be a completely compatible merge. Yay, totally fine. Does that make sense? Right? All between any points, as long as between those points they are completely connected, you can merge them as a subgraph. So if you notice, D and E, it's completely connected. It's only 2 points. That's trivial. That's normal, right? I can merge A, B, C because there's a line between all three of them. It's a completely connected graph between A, B, and C. But I could not merge A, B, C, D. Because, for instance, D can't be B, and D can't be C, right? It would not be completely connected between A, B, C, D, so I can't merge A, B, C, D into one state. So I can merge them this way because these are completely connected.
I mean, so in theory, we could merge and form that.
So look, there's other ways we can do this, right? I'm hoping this shows up. This is going to be green instead of blue, right? Could I merge just B and C and then merge A and D if I wanted? It's legal, right? Could I merge ADE?
A, if it's doesn't.
Yeah. So you can't do it. But we could do this, right? And maybe this ends up being easier for me on whatever state transitions or whatever I want. It might be better to merge BC and AD,
So
right?
it's supposed to, it's between 2 points is a line, the first one is a triangle, and 4 points is a square.
I said, yeah, I got the separate diagonals to it. Right? Well, that's why I'm saying completely connected graph. Okay? That it's the easiest way to do it, right? Between any set of points you want, if all the connecting lines between every point and every other point in that little subgraph, if they're all, we call that completely connected. Every one of them is connected to each other in one line. You can merge them. You can merge them. It doesn't mean you have to. It just means you can. If any of them is missing something, you can't merge them. Does that make sense? Fine. So I specifically made this one in advance before I got down here, so I had a bunch of things I couldn't merge. Right. So that's what I was saying. Rather than trying to find a problem that had what stupid merges I could do, I completely made up a problem just so I got a bunch of good merge states. Right. And there were some contradictions. I can't take the merge state. I can't do every pair with has merged. It's just not possible. If I merge D and E, I cannot merge A and D. And if I merge A with either B, C, or both, I cannot merge A and D. And it's just, there's limitations. So just because they're compatible in this case, I can't do every pair of these compatibility because there's some that just won't let me merge them down. So that is easy to see in the picture. I guarantee you it's not so easy to see in that table. So the pairwise table lets you see, kind of like all the details. It's really good for organizing your check and seeing what works. But to take a look at bigger interactions, only the graph does. And if you put them on the outside of the circle, it's just easier to see. If you ever try to do your own graphs and start getting completely connected and the lines go outside, it can get really ugly really fast. So that's why I tend to like this, because it puts all the connecting lines inside the circle, so it just makes it easier to solve things. Yeah.
So this is just the case of like position with the question.
Exactly, that's what state reduction is.
So is there an equivalent of identifying from the very get-go that like your transition graph is like what would you consider like what's the one where like there is no reduction in the smooth state, but there is no
So you have to analyze. And usually when you first get these in a real problem, there's going to be a customer requirement which generates those use cases. From a bunch of use case text lines, I mean, maybe you're better at this and you might have some gift, but I can just say, I can't look at a bunch of customer requirements unless it's a pathetically simple, obvious reduction, and where you just see, hey, they have the same requirements twice. I think if you go, no, that could have been reduced. But in most cases, it's like pages and pages of crud, right? That you get out of these. So it's really hard to tell in advance. And that's why, to me, I find it easier. Okay, I got a new state, and I just keep adding it in the column, and how does that one have to move? And I draw those arrows in this kind of organized fashion. And now I get a bunch of these little primitive states, right, that are based off customer requirements of, what does it do under these cases? And usually there's only a few transitions that can happen inside them, so I can draw them up easily. I then turn it into a regular table, and now I need to compile one, but the table's huge. So again, you might be able to look at it and just recognize it. There are some lucky cases where that happens, but systematically, that's really hard to do, right? So the whole purpose of that kind of triangular block stack is to give you an organized way to check everything. I guarantee you when you're looking at that, it's super easy to forget to check one of them. If you make the little stacked block triangle, you're not going to forget any of them because they're all labeled for you. Just go through it. I always tend to go top to bottom, left to right. You can do it whatever order you want, but be systematic would be my statement to you. I don't care. If you like going, bottom to top, right to left, knock yourself out. Just don't pick some kind of random junky thing because you'll never know. Right? In theory, if there's nothing in there, you haven't been there, so I theoretically could do that. But it is easy to miswrite something, and so if you're doing kind of a systematic check, it's kind of better to go. I'll be honest, if I was doing this for like some professional situation, I actually sit with a highlighter, and I go from the previous table and I highlight the thing that I actually worked on, so I can just see, oh, I did that transition. And I literally done. So that way, if somebody asks partway through something, you ever have halfway through a problem and somebody asks you a question, right? Like, dang, where was I? That. So again, a lot of these are just some systematic ways to make sure you're careful, right? Asynchronous is devil in the details, right? Because any small thing can screw it up. Each step is not horribly complicated if you realize the problems that can happen. You don't want glitches, you don't want races, right? Particularly critical races, right? Glitches I can remove with Cardinal maps, problem solved, don't worry about it, right? Just do K-map design or Vygotsky, which is the equivalent, right? And we've seen there's fast ways to do that. Well, what the other thing that I can do, well, to take care of the races, first I'm going to want to be able to do transitions. That's what we're doing with these primitive states, right? I first remove the input races, and then I'm going to make sure when I do my design of my states and I actually change them from letters to codes, I'm going to pick a code system that doesn't give me a race. Right? Good? All right. I'm not sure if I'll get to the second one now just because of our timing. What I will do is I'll put up videos for the second one. So if you want to see a second example of me doing some of these, I'll put a series of little videos and I'll chunk them up. So I have some of another example I was going to do from you where I recorded individual separate video chunks. So I'll just post those immediately as an example too. Feel free to skip through it shamelessly, run it at double speed, and you'll just see me again walking through all these cases. So I'll just give you a second one. It's not an obligation thing, but I think it does help. So we've now seen how we can do these. I can reduce, let's say I do the blue combo, this one and this one. Just because I want to make it as small as humanly possible. Good? So I need glasses to actually see what that is. So I need to now take this table and do this combination. So I'm going to, in this case, make A, B, C. That's a new state. I have E, F. I'm going to call that G. And D and E, I'm going to merge together. That'll be my new state H. And then F is F. Fair? Let's do it. We good? That's kind of that's ABC just means that, triple blue circlement. D and E, that's this one. I can't make both of these show easily, so just kind of remember these. I'll write it back up here. A, B, C is my G, and D, E is my H, and F stays the same. All right. So now I'm going to simplify my table. And so now I've got G, H, F, and that's all I need for this. And you'll watch, it's going to fill things in because I've got a lot of requirements now. So G is going to be A, B, and C. So that says A stays A. That's got to be here. So that's got to be a G now because A becomes G. Output is 0. And we can note, A, B, C, there's no problems with making that choice. The next one, B is becoming G, and that's stable. And the output is 0. Again, totally compatible. All right. The next one, C, 0 is fine, which means it's now G, 0. Good. Last one goes to D, but D is H. So it's going to H, and I still don't care what the output is. We feel good about, I reduced the first three down to this. Now I've got H, which is D and E. I'm going to square box these, again, to make it a little bit easier. All right. The first one, it goes to A, which is now G. And I don't care what the output is. All right. The next one goes to E, right? But E is H. So it's staying at itself, and I'm outputting a 1. The next one, it goes to F, which stays F, and I don't care what the output is. And I've got D goes to D, which is H goes to H. And it outputs a 0. Fair? All right. Last one, F is itself. F, 1. So now I've got a pretty dense table. I've just got a couple outputs that are unique to them. And I can decide what do I want to do with these. Now, looking at this, is it possible for this to be a more stable one of outputs dependent on states? If I'm in H, that's what the row is saying, is the output constant for that state? To like totally fine with G and F, okay? Those can totally be Moore style states, but H cannot. This might be a reason you might say, well, I really need more states, in which case you would want to merge those two. So that would be an alternate reason to merge things, is because maybe you want to force more states. H has to be a Mealy state, because the output has to depend not only upon the state, but what is the particular input area. So if I'm in H and it's 0, 1, you must output a 1. If I'm in H and it's a 1, 0, you must output a 0. It's unavoidable, right, that you get a Mealy. Does that make sense? Okay. So looking on these, now I have to go to doing some design. Now this is 3, right? So let's think about what ways could I encrypt states. Because at some point you've got to turn these into numbers. because you have to encode things with zeros and ones. But there's a lot of 0, 1 patterns out there. Right? So let me ask you, what type of encoding patterns, what systems that you can number states? Binary, right? So I've got one system, binary, right? That's the 0, 0, 0, 1, 1, 0, 1, 1, right? 0, 1, 2, 3. I can just do normal binary numbers. What else can I do? What's that? You could stand gray. I could number these gray code style. We're just right now listing, right? So 0, 0, 0, 1, 1, 1, 0, right? Again, it's got that same number of bits you need to encode a certain number of objects, but it's a little more obvious to see where those transitions are. Now, some people still like binary because it's easier to read out and things of that sort, right? These are not trade-offs. We're just analyzing. Is there another system we can use? One hop. What's one hop? Yes. There's a bit for each. So in this case, I've got 3 states. So one hot, right? Think hot, like if I said I have a hot line, it means it's got power, right? So it means one is powered up at a time. So I've got 3 states, so I would need 3 bits. So I can have 0, 0, 1. But only one can be hot, so I also have 0, 1, 0, and I have 1, 0, 0. That is one port. Okay? Now there's an awful lot of unused codes in here. Okay? But this one is actually pretty stupidly easy to design to. Believe it or not, this is the preferred method for automated systems to design on. If I do gray code, and I got like these 3, right? I can say here, well, gray code's kind of nice. I can make this 0, 0, 0, 1, right? I can make this one 1, 1. In this case, that'll actually work quite nicely, right? Right? Because in this case, I only go from 0, 0 to 0, 1, right? Here I can go from 0, 1 back to 0, 0 or to 1, 1, and I never leave 1, 1. But what if one of these states went back to G? We got a race. Is that good? No. So now I got, if I'm doing straight gray code, and I'm looking at 3 of these states, it's going to be very hard to force them based on the condition. I can start making new states, like the intermediate one, to avoid the race. There are ways I can handle this. In this case, it's kind of tough because my 1, 1 state is you don't leave it unless you reset the system. So who cares? So what we do is we can now we generally make a transition requirement if I did one home, where I just say, hey, look, if this was, my 0, 0, 1, this is 0, 1, 0, this is 1, 0, 0. When I want to switch here, I just say automatically when you're going here, I'm going to turn on the extra bit and then turn off the push. That's trivially I just slow it down. I force an intermediate state. But it's so automatic that it doesn't really take a lot of thought from this, right? If I want to switch from here to here, again, all I do is I turn on the bit I want to go to, right? And then I turn off the one I'm coming from. That sequence is trivial. You cannot run into problems. Right? The only way you would ever have where it's ambiguous, because I can do this, if I'm in one column, I'm transitioning one way. You can't go back and forth. That's a cycle, and we don't like cycles anyway, so we're removing those. So there's no reason you'd ever come back and forth, so you know which one was first when you're in a state based on the inputs. It's unambiguous.
turn one on to turn it off and then turn the other on? Is it just because it has?
Because then I will go through 0, 0. And then I don't know which one I was going to, right? These are states. Implicitly, what I'm doing, if I'm doing one hot, is I've got the 0, 0, 1 state, all right, which is 0, 0, 1, comma, 0. Let me do a slash now because I'm kind of looking at this out. All right, this is my G, H. Let me just do G and H just to demonstrate what I'm saying. So 0, 0, 1, we're replacing them by their numbers, all right? And I'm putting the slashes in because now I've formally numbered the whole thing up, so I'm going to a more normal state area. All right, so this is just rewriting the table at the moment. And H, which is 0, 1, 0. And right now I don't care. I'm going to leave it blank because I get to pick it. All right, and in this one, it goes to G, which is 0, 0, 1. All right, and I get to pick it. This one stays at 0, 1, 0. All right, this one's going to go to 1, 0, 0. And that one's staying at 0, 1, 0. And out point is 0. Now, what I'm going to do, when I see this, I'm going to this. All right? It's transitioning to a different one. I'm implicitly making an intervening state. All right? And in this case, I'm going from here to here, right? 0, 1, 0 to there. So, oops. I'm making an intervening state where both bits are off. Right? This is not going to, I will make you stable states like this. So what I'm saying is I'm going to turn this one so it goes here and this one so it goes there. So you implicitly from this, you'll go here and from here you go there. And it's a done transition. I'm going to do it in 2 steps. You're only going one way, you're not going back and forth in any column. Okay? So there's no ambiguity. If everybody went through 0, 0, then every transition would do it. See right here, this one, it's going from 0, 0, 1 to 0, 1, 0. So it's got to go through the 0, 1, 1, and its destination is going to be that. So I intermediately stick that in. So notice in both cases, I'm going to 0, 1, 1, but they're in different columns, so who cares? It's unambiguous which way I'm going. Does that make sense? Now, in this column, if I go to any other row in the same, right, so when I'm going between 2 rows, there's no ambiguity, and that's the only way I can get to this middle state. Once I add some other state in here, right, if it has a transition in any common column here, then I'm in deep trouble, right? Because if I go to 0, 0, 0, because then everybody's going to 0, 0, 0, and you don't know where you came from, right? So that's the problem with 0, 0, 0, is that if there's anybody else in the column, you can't distinguish it by what the input is. I can tell the difference between these two because you know, and then I could only be in 0 and 1 if I was moving between these 2 states. So I don't care about anything else in the table. It's only between those 2.
So you add transitory states in order to reduce ambiguity. Did use your 0, it would increase ambiguity for reduced states.
It would reduce the states, but now it is ambiguous, so you don't know what's going to happen. And we're trying to remove that. This is a systematic pattern that can generate an error and can generate a risk. So it's stupidly done and simple. The only problem with this is you end up having a bit for your state. So you need more bits. Right? You know, that's the trade-off. These ones are as a log of the number of states, originally we just growing linear. But if you have 2 states, who cares? You want how it's simple as stuff. Right? I mean, it's stupidly simple. I don't even actually like these. I think the computer do it for me because the answer, once it's systematic and you can describe it as a systematic, why should I ever do it? Uh, I want to be lazy and efficient, right? The smart lazy, right? There's a smart lazy, there's a dumb lazy. Smart lazy says, turn it over to something that will systematically do that pattern. I don't have to do that. I can't make any mistakes. And it will just work. Done. Program it over. That's good. Efficiently, it just doesn't get anything done, right? So, in this case, I think, oh, I'm hot. It's over with. Right? Now, I can make this one smaller if I go, oh, in this case, there's no transitioning out, so what do I care if it's next to each other? Right? So again, you can watch and see which transitions happen, and you just make sure that all the transitions are one bit hop away, one bit hop away. I go, ooh, I can do great code for this. No. Right? So that makes my life very easy. Right? And it's small. Yay, little more work. But in this case, one work always. Right? And it is great code for just because nobody ever uses that. Right? So G has to be next to H because the transitions back and forth, but only F only needs to be next to H. So I just, when I'm listing who has to be next to each other, right? G has to be next to H has to be next to G and F. F only needs to be next to H. So that forces H has to be in the middle. Right? Does that make sense? So I have to think a little bit more when I'm doing grade code. Well, it just says you have less skips. Make sense? What do you do? One, stupidly easy, right? Yeah. It would have two transitions to achieve that, right? You always have two transitions. But everybody has two transitions in the past. What about a phenomenon that is so short? I can call it one transition. Got to go to great code and figure out a clever way to do this. So give me an example, I'll give you one of those. Where I can force it, even though it's complicated, I can force it to only do a single transition. But I don't know what some other conditions, like to split states, all kinds of stuff like that. So there's a little more work involved in it, some thought, and I'll just give you those that process. But this gives you the basic one. Coding methods, and you've got at least three basic code methods. You've got the foolproof system that types one yay, and the other one usually you only use great code. But you do that to, if you need something really small, something really elegant, then you do the extra work. Good? Awesome. So watch all, literally, I've already got them. So I'll drop them up there for you. It'll be up there. Have a look. If you got questions, you are welcome to come up.
Do you think you can give like an example